Greetings, this is the presentation of our work, Large to Small Image Resolution Asymmetry in Deep Metric Learning. In deep metric learning, input images are mapped to high-dimensional vectors, called embeddings, such that the images that are relevant have similar embeddings. For that, we use deep convolutional networks. The target task is image retrieval, which consists of a large collection of database images and query images. We rank the database according to the distance or similarity between database embeddings and the query embedding. Let's take a look at how performance is affected when we train at a particular image resolution, but test at different resolutions. A fully convolutional deep network allows us to do that. Using slightly larger test resolution than train resolution improves performance, but much larger test resolution hurts. However, increasing the training resolution allows us to increase the testing one too and further boost performance. We conclude that large input resolution and details matter for fine-grained recognition. Yet, the extraction time grows quadratically in the input resolution. How to maintain gains of large resolution while keeping low extraction time? We take advantage of the two types of images involved in image retrieval. We use large resolution for database images which are pre-processed, but decrease query time by processing the query image at smaller resolution. For instance, when querying from low-resource mobile devices. This, however, introduces asymmetry, which in turn harms the retrieval since there is a discrepancy in the two resolutions processed through a single network. To mitigate this, we process the two types of images with different models that share the same architecture. Here is how we train the query network given a fixed database network pre-trained with a supervised metric learning. We use a knowledge distillation approach where the database network is the teacher and is fixed, and the query network is the student. Using the same architecture allows us to initialize the student with the parameters of the teacher. Each training image is first downsampled to small resolution, and the exact same augmentations are applied to both images of large and small resolution, which are then processed by their respective models. Resulting embeddings have the same dimension, allowing us to compute pairwise distances or similarities within teacher embeddings, within student embeddings, and across teacher and student embeddings. We refer to the last ones as asymmetric distances. Here is a 2D toy example to demonstrate the different losses. For the same augmentation, the object in the two images differs only in scale and is processed by a different network. We show embeddings for 3 augmentations of the same image. For the asymmetric retrieval to work, the embeddings should be as close as possible, which we enforce by a loss penalizing according to the asymmetric distance for the same augmentation. Pink triangles move towards the corresponding green crosses. This loss operates according to absolute embedding positions, reflects the objective of the target task, and does most of the work. We use 2 additional losses that operate on relative embeddings positions to target better generalization. One that enforces pairwise distances within student embeddings to match those within teacher embeddings, and one that enforces the asymmetric distances to match those within teacher embeddings as well. We evaluate on 3 fine-grained datasets with ResNet50 backbone. Results are measured in mean average precision. Here we see 2 baseline models trained with supervised metric learning on 2 image resolutions. The naive way of using resolution asymmetry is to use the same network to process queries at low resolution and database images at a large resolution, which performs poorly. The model trained with our distillation approach evaluated in the asymmetric setting almost fully recovers the lost performance. Despite our focus on the asymmetric setup, we evaluate the low-resolution student in a symmetric way. The results indicate that instead of supervised metric learning on small resolution, it is significantly better to first perform metric learning on large resolution and then distill with our approach to small resolution. You can check our paper for extensive results and our online code to reproduce them.